Indy Autonomous Challenge, Indy means that Indy car, but they replaced the human drivers with AI software.
We use a vehicle with the horsepower that professional race car drivers use, with sensors and actuators that allow us to control it via drive-by-wire.
And now university teams program this car to compete for the fastest lap time with the AI software.
It pushes us to the limits of what our algorithms can do.
Once you have that high speed, it's going to amplify whatever challenges you had. That's very unpredictable. So it's a good motivation for us to think about what kind of gap we have between what we do in the laboratory and what we need in the real world setting. Once you have autonomous vehicles navigating very complex environment, you really have to push the envelope of what you can do in terms of autonomy software.
Because we are moving at 150, 170 miles per hour, you cannot afford to have your code operate at any speed other than lightning fast. We're talking about differences in hundredths of a second that can move the car tens of meters, and that could be the difference between a beautiful corner or a nasty spin.
Coming into Laguna Seca. It is kind of wet out there, so I'm kind of concerned about that, but should be cool.
About half an hour before our race slot, we head over to race control. We set up, make sure that our telemetry is showing that everything is working the way that we expect. You know, you push a button in your laptop and then the car slowly rolls out of pit lane. We watched our car do its out lap. It looked beautiful. The first lap that we took on also looked great. That second lap was much, much faster. But when we took on the Corkscrew, we experienced severe wheel lock.
It's a very, very complex mechanical and dynamical systems. So when you actually increase the speed on the corners, then it's going to put the cars on edge of traction limit or friction limit. We really pushed the envelope. We got the fastest lap time in the first lap and second lap.
However, on its third lap, I notice in our telemetry that our tires are locking. For a fraction of a second, I see a car sliding past the corner. I hear in the broadcast,
"He's not come around yet, Rob. I think there's been an issue."
You know, they're all asking, "Where's the car?" Meanwhile, I feel this pit in my stomach. I know exactly where the car is.
So Caltech Racer's 2 lap times, they were the fastest, but they exist no more.
Other teams have been doing this for 5 years. Because we've been only working on this project for 9 months, I think we have a very respectable performance so far, but still we have to still improve our method.
It is exceedingly rare in research that you get to work on something that is so directly applied with such concrete real-world consequences.
Autonomous racing is one application, but once you develop the full autonomy stack that can drive and avoid an obstacle, mapping the unknown environment, this kind of results and the method can be applied to spacecraft, planetary robots, and so on.
Autonomy is everywhere in our society, and the types of algorithms that we develop, for example, for fault detection, for fault recovery, are things that could apply to oil rigs, like to spacecraft. There's no limits, truly, to where rapid response to failure and changing conditions will apply. I can't say that I'm satisfied with our performance. I think we left some performance on the table. But what we also did is prove to everyone that Caltech means business and that we're coming for them next time.